Hello guys, today in this video we are going to discuss about metal semiconductor and semiconductor heterojunctions. So basically this is known as Schottky barrier diode. So today we are going to discuss about this Schottky barrier diode or metal semiconductor junction. So we will start with ideal energy band diagram for the metal and the semiconductor. Here the semiconductor I will choose is N-type semiconductor. Okay, and before contact what will happen and after contact what will happen, what are the variables that we should know to understand the metal semiconductor junction better and the characteristics of metal semiconductor junction. So to start with this, we will define a vacuum level here. So let me tell you what is vacuum level. So we will define this vacuum level as the reference energy level, and it represents the energy of an electron outside the solid. Okay. So here first thing is that, and then let me draw the metal side. Suppose this is the metal side and the other side is the N-type semiconductor here. Okay, and the Fermi energy level, okay, so are the most important characteristics, okay, or the parameters that one should know. So this is the Fermi energy level of the metal side, as you can see, and this is the Fermi energy level of the semiconductor side. So this Fermi energy level of the semiconductor side here I have shown you at a higher position. Okay, so this is at a higher position. EFS is at a higher position than EFM. And then I showed you the energy gap between the vacuum level and the Fermi energy of both metal and semiconductor. So we will define this energy as the metal work function. This side I wrote it as E phi m, phi m being the potential, E is the electronic charge. So electronic charge multiplied with the potential gives us the energy. So in terms of energy I have written. So okay, and similarly here I will write E phi s. Okay, this is the semiconductor work function. Let me define what is semiconductor and metal work function. Basically, work function we will define as the amount of energy required to elevate an electron, to lift an electron from its Fermi level to outside the material. That is the vacuum level here. Okay, that we considered as a reference energy level. Okay, so this is one. Then, as we said, N-type semiconductor, the conduction band will be close to the Fermi energy level. So this is the minimum value of the conduction energy band, and this is the valence band. Okay, so this is the energy band diagram for N-type, and here this side you can see the metal. Okay, metal side. Okay, so few more variables. For example, what is electron affinity? Okay, electron affinity, we will define this as the electron affinity, the energy gap you can see right now. So this gives you what? The amount of energy required to remove an electron from the conduction band, minimum value of the conduction band or the bottom of the conduction band to outside, which is the vacuum level. Okay, so that way we can say this is the electron affinity. Okay, now in this case we consider the metal, okay, and N-type semiconductor where the condition is phi m is actually greater than phi s. As you can see, the Fermi energy level of the semiconductor is at a higher position than the Fermi energy level of the metal. Okay, so in terms of potential we wrote this way, phi m is greater than phi s. Now what will happen if I will make a contact between this metal and N-type? So first thing we know, as there is the position of the Fermi energy level is different in both metal and semiconductor. When we will combine, it will attain the achieve the thermal equilibrium condition, and hence the Fermi energy level of the metal and the semiconductor will lie on the same line. So will be constant throughout. So to make that, what will happen? There will be bending of the conduction band and the valence band as well. So when it will be constant, the Fermi energy level of the semiconductor will go down and the Fermi energy level of the metal will go up, so that it will be constant throughout. And first thing we need to show is the Fermi energy level will be constant throughout. Then the initial point here, you can see the starting point of the conduction band, which will be like this, okay, somewhere here. Okay, so this was the starting point. Then what will happen? The conduction band will bend, right? As it will, Fermi energy level will go down, conduction band will go down and will bend downward, and the valence band will also bend downward. So we can see the band diagram will be like this. It will go this way, and this is the conduction band. Okay, this is the Fermi energy level now, which is the same Fermi energy level of the semiconductor and Fermi energy level of the metal are at the same, value. Okay, and then the valence band will also bend accordingly. Okay, little more gap you will see. So we'll go and then this. Okay, so this is our valence band. So this is the structure. Now let us define the variables. Okay, that some more variables that we will introduce now. So one thing is the metal work function, which is exactly the same vacuum level. This is our vacuum level. So vacuum level and the Fermi energy level, this gap is your E phi m. So let us mark it as E phi m. And then now one more variable I'm going to introduce, which is the Schottky barrier height. Schottky barrier height, we will write it as E phi B0. I will define everything. Okay, so what is E phi B0 here? Schottky barrier height. This is the potential barrier or the energy barrier faced by the electrons that is present in the metal, okay, trying to move to the semiconductor. So this is ideally the barrier height faced by the electrons moving from the metal to the semiconductor side. Similarly, what is the barrier height that will be faced by the electrons present in the conduction band of the n-type semiconductor to move from the semiconductor side n-type to the metal side? Okay, that is the built-in potential barrier, which we have already done in PN junction diode. So this will be the potential barrier faced by the electrons moving from the conduction band of N type to the metal side. Okay, so this is one parameter. And EC minus EF. Okay, this EC minus EF is also known. We have already derived this for semiconductors, and this value we will write it as E times phi n. Okay, E phi n is EC minus EF for the semiconductor, which is also a known parameter. Okay, so these are the parameters that we will come across. Now you see how we can write, phi B0 depends on what. So here if you'll see this phi B0 barrier height, if I'll write phi B0, we can write this as, this, let me highlight this, phi m here, and then, yeah, one thing, this is our E chi remains the same. This chi, which is the electron affinity, E chi, electron affinity, okay, it is independent of what? Independent of doping level. It depends upon the original position of the conduction band, and from there to the vacuum level, to the vacuum level, it is independent of the doping profile, okay, or the doping concentration. So now if I relate this to phi B0 plus E chi, or the electron affinity, E phi B0 plus E chi gives us E phi m. So we can write phi B0 is equal to phi m minus chi. That is one we can determine, okay, using this phi B0, which is the ideal barrier height or Schottky barrier height, can be determined from the metal work function minus the electron affinity of the semiconductor. That this difference gives us the ideal barrier height or Schottky barrier height. This is one thing. And then the second thing is the built-in potential barrier, that also can be determined. You can see VBI plus this E phi n gives us phi B0. Okay, so we can determine VBI from phi B0, that is Schottky barrier height, minus phi n, right? So phi n, and this phi n is nothing but EC minus EF. So phi n is equal to EC minus EF, which is a known value. We have already determined this for, in the semiconductor. So it can be written as actually KT by E, okay, ln NC by ND. Sorry, here it is KT ln this, because, okay, in terms of potential, if you write, this is, okay, E phi n is equal to, in terms of energy I'm writing, I will have to multiply this E, electronic charge. So E phi n is equal to dc minus EF, which is kT ln Nc by Nd. So if you are writing in terms of only phi n, divide by E, so it will be kT by E ln Nc by Nd. This Nc is actually the effective density of states in the conduction band. Okay, and Nd is the doping concentration. Okay, so donor impurity concentration Nd. Okay, using this, we will be able to find out this VBI. Phi 0 minus phi n is VBI. Phi V0 is equal to phi m minus chi. Okay, so these are two things that can be obtained. Okay, so once you are aware of the the ideal energy band diagram, when we combine the metal and n-type semiconductor, where we consider phi m is greater than phi s, it looks like this. Okay, using this, we can also extend it to what to biasing. Okay, so biasing means what? We are going to connect it to some terminals, okay, of the potential, positive and negative terminal of the potential. For example, here if you will connect, okay, or we will apply a positive voltage to the semiconductor, okay, positive voltage to the semiconductor, with respect to the metal, then what will happen? This is connected to positive terminal. So what will happen here? The Fermi energy level, okay, Fermi energy level here will go down, okay, and the potential barrier will increase, right? So the depletion region will increase. So this will become VBI plus VR, okay, E times VBI plus VR. This will be right. And whereas this E5B0, that is the Fermi energy level metal to the vacuum level, or the potential barrier, sorry, Fermi energy level to the to this junction here, right? So which is the ideal barrier height or the Schottky barrier height, that remains unchanged. Okay, similarly, if you will give a negative potential to the semiconductor side as compared to the metal, or with respect to the metal, then what will happen? This Fermi energy level will go up, and what will happen? This will be replaced with VBI minus VA, where VA is the applied voltage. So E times VBI minus V, and the potential barrier here from the semiconductor to the metal side will decrease, whereas this E5A0 remains same. So in both the cases here, okay, depending upon the bias, okay, whether it is reverse biased or forward biased. Reverse biased, when the built-in potential barrier from the semiconductor to the metal increases, okay, that is what is reverse biased. When the n type is connected to positive, okay, and when the n type is connected to the negative terminal, the the potential barrier decreases from the semiconductor to the metal side, and we call it as forward bias condition. Okay, so now this is the case. If I will draw it for reverse and forward bias, then we can show this way. This is our vacuum level, right? Okay, sorry, this is the vacuum level. This is the original value of the conduction band. Then we said the conduction band will bend more because the Fermi energy level is going to shift more. So the Fermi energy level will now come down because this is in non-equilibrium EFS. Okay, because we connected it to the positive terminal. So N type connected to positive terminal, right? So this is Fermi energy level of the metal. There will be no change. It remains the same. Okay, so here this remains the same as E5B0, right? And this became increased. It was earlier EVBI, now it will be EVBI plus whatever reverse bias you gave, voltage you gave, right? And the valence band will also bend accordingly. I mean, exactly the same as the conduction band. So EV. Okay, this is the metal side. Okay, this is the reverse bias condition. And forward bias, we have same the vacuum level, but this side is now connected to negative terminal. So the bending will be less because the Fermi energy level here will go up. So here the bending will be less. The space charge width, okay, is more in the reverse bias case. In the forward bias case, it will be less. So Fermi energy level will be little up here. Fermi energy level of the semiconductor conduction band of the semiconductor, band bending of the valence band is here. Okay, and the Fermi energy level of the metal is as it was earlier, so it remains the same, right? E5B0, E5B0, and then vacuum level. Okay, so E5B0 remains the same. So this is how it looks. Then your potential, built-in potential barrier will be EVBI minus VS, so it is reduced. The space charge will also be reduced. So for the electrons which is coming from the conduction band of the semiconductor to the metal side is decreased, right? Whereas here in this case, in this reverse bias case, you can see the potential barrier from the semiconductor side to the metal side is more. Okay, this is how the biasing works. Okay, now if you will extend it to suppose we will take metal and n type semiconductor, but the condition here is now phi m is less than phi s. You can draw accordingly. So suppose we have this vacuum level before contact. If you draw, it will be easier for us. Okay, we can easily draw what will happen after contact. So let us draw the energy band diagram for the n-type EC we got, and then we got EFS, Fermi energy level of the semiconductor, and then the valence band. Okay, and here we said phi m is less than phi s, so the Fermi energy level of the metal will be at a higher position, EFM. So these are the values, E phi m, and here this is your E phi s, right? And this is your E chi, the electron affinity, right? And when you make a contact in between, what will happen? For electrons from the Fermi energy level, from the metal side, that are higher position, you can see the Fermi energy level is at a higher position. So electrons will move from metal to the semiconductor side. So what will happen? This semiconductor side will go up and it will go a little down. So this way, so thermal equilibrium will be achieved. So now after contact, you can see the Fermi energy level of both the sides. Okay, EFM and EFS is this, and there will be band bending accordingly. So it was the original position of the conduction band. Okay, and then it will go up a little bit and then will be like this. So this is the new position, okay, of EC, and hence your valence band will also move accordingly. So this is your EV. So this is the case, okay, and the depletion width, depletion region will be like this. Okay, this is n type and phi m is less than phi s. Similarly, we can draw for metal and a p type, for the condition phi m is less than phi s. Okay, so exactly the same way we will draw separately. Okay, so p type, we know the position of the conduction band and all. So let us draw EC, this is the conduction band. Okay, and then the Fermi energy level will be closer to the valence band. So this is EV. So you got your EFS somewhere here close to the valence band. Okay, and now we have EFM, that is Fermi energy level of the metal. We consider this. So here is our E phi m. We considered phi m is less than phi s here. It's evident from the diagram. You can see that this is E phi s. Okay, now when we will combine this, what will happen? When we will combine this Fermi energy level here, you can see is at a higher position, but we need to consider for p type, it is we will consider the valence band, we will consider the movement of the holes here. Okay, so accordingly we will see what will happen. So Fermi energy level here will go up and this Fermi energy level here will go down. So the Fermi energy level in the entire system will be constant throughout. So we got this as EFS and this is our EFM, first thing, right? As it is going up, Fermi energy level of the semiconductor side, your conduction band will also, original position was this, and then it will bend accordingly, will move upward, and then this. Okay, so you got a little bit more because we need to show the p type as well here in this diagram. So I will show you this Fermi energy level from, sorry, from this position. Suppose, okay, this is my conduction band, and the valence band accordingly will bend, okay, will be close to the Fermi energy level, right? And this is the potential barrier, okay, created for the holes. Okay, holes are the charge carrier over here, so we need to show that way. EVBI over here, okay, that we can show. This is our EVBI, the built-in potential barrier. Okay, and the phi B0 will be this. From the metal side, what is the barrier height? So this we will consider in the valence band, we will consider for P type. So accordingly, your ideal barrier height will be this E phi B0. This is for P type. Okay, so now the depletion region is created over here, okay, for P type, and phi m less than phi s. Similarly, we can do for metal and P type where phi m is greater than phi s. Let us draw it and see what we will get. So metal and P type semiconductor, but we considered the case of phi m greater than phi s. Okay, phi m greater than phi s. Again, we will draw this way before contact. The P type where we got EC and we have EV. Valence band Fermi energy level is close to the valence band EFS in P type semiconductor, right? And the Fermi energy level of the metal, now we are considering that phi m is greater than phi s, so somewhere here. So EFM, right? So in the diagram, it is evident that you have phi m greater than phi s, okay, E phi s. Now, what will happen when we will combine? Okay, let's see. So this is the case. Okay, here you got your conduction band. Well, now here you can see the Fermi energy level is at a lower position here in the metal, and semiconductor it is at a higher position, right? So what will happen? Electron will move from the semiconductor side to the, sorry, here we are talking about holes. So holes will move right from the valence band to the Fermi energy level. So what will happen here? First thing is to make the thermal equilibrium, where you need to keep Fermi energy level of the metal and Fermi energy level of the semiconductor at the same value. Right now here Fermi energy level is going down and this will go up, right? So this way we got it. So accordingly your conduction band will bend. Okay, so conduction band original value, conduction band will bend. So this is your EC and this was your EV original position, and EV will also bend accordingly and this way. So this is your EC and EV you got. Okay, so the depletion region that is created over here. Okay, now if you'll see the barrier height here from the metal side, you will see this is the barrier height because this is the contact. Okay, for the valence band we have considered P type, so we are referring to valence band. So this is our E phi B0 barrier height has reduced for the P type and phi m greater than phi s, and the built-in potential barrier also you can see from the semiconductor side. Okay, so from the semiconductor side, what is the barrier height? What is the potential barrier here for the semiconductor side? Actually, it's very, you can see almost nothing, here. It will not face any barrier while moving. So we will discuss more about these, contacts, what is rectifying, non-rectifying contacts and all, ohmic contacts and all. So in that video, I will clear these things. So fine. So this is what is the barrier here, E5 V0, that is called Schottky barrier height, you can see. Okay, and the potential here you will see is this. Okay, so this is all about the energy band diagrams for different metal and semiconductor junctions, depending on the phi m and phi s value, whether phi m is greater than phi s, phi m is less than phi s, or the semiconductor chosen is N type or P type. Okay, so we will discuss more about the contacts and the IV characteristics as well as junction properties in the next video. Thank you for watching.